Welcome everybody to our calculus notes for 2.6 on related rates. So this is one of our first applications of calculus that we're going to look at, and it comes at a really good time, and you're going to see why in just a second. So just a little review. Calculus is the mathematics of change. So that's what we're studying, how things change. And we have learned that the derivative is a measure of how one quantity changes as another quantity changes. Okay, so we find like the derivative of y with respect to x. So as x changes, how is y changing? That's what we were looking for. And we've also talked about the derivative equaling something called the rate of change. So the derivative is the rate of change. And we've spent a little bit of time now learning how to find these derivatives. Now here's where related rates come in. So if two quantities change in relation to each other, both with respect to time, then their rates will also be related with respect to time. Okay, you got that? So we have two quantities that are related, and they're both related in terms of time. And what that means is their rates are also going to be related in terms of time. So in other words, if we have two functions that vary with time, and these two functions are related to each other, then their derivatives, so the derivatives of the function, are also related to each other. Okay, so if we have two functions that equal each other with some sort of relationship, then their derivatives would also equal each other with some sort of relationship. So why is this a good time to talk about this? Well, we just studied implicit differentiation, and this is what we're going to use it for. So implicit differentiation allows us to find the related rates. Now the reason this is going to work is notice everything here is respect to time. So it's all as it relates to time. Now if we look at these two quantities are not in terms of time. And so the implicit differentiation is going to allow us to find these derivatives even though time is not in our quantity or in our function. Alright, so let's try our first example here. It says, suppose x and y are both differentiable functions of t. So what that means is x is really some function in terms of t. But we're just going to write it as x. And it's going to kind of have this idea like we were using with the u's, that x is really wrapped up and it's a function of t. Now it says y is also a differentiable function of t. So y is some other function in relation to t. Okay, you got it? Now, it says that they are related by this equation. So this describes the relationship y equals negative x squared plus 10. So how are they related? Well, it looks like x right here, if you would square it and take the negative and then add 10, that would give you y. Okay, so that's always talking about the relationship. Now, what we want to do is find dy dt when x equals 2, given that dx dt equals 3. So basically, what we're doing here is we're giving you a couple parts of the puzzle, and we're asking you to solve for this right here. Here's our function. Here's how y and x are related. And it says when x equals 2, and you can see the crosshairs here, right here, how fast is the y value changing with respect to time when we know that the x value is changing at a rate of 3, and that's units per second, could be feet per minute, however. So that's what we're thinking here. So we know that this is changing at 3 units per some amount of time. We want to know how fast is the y changing. okay, at that specific moment of x equals 2. Okay, so for this we're like a projectile, and we knew its horizontal velocity was 3. Okay, what would its vertical velocity be? And that's what we're trying to find. So what we're trying to say here is if we know the relationship of the equations, then we can find the relationship of the rates by differentiating both sides, but it has to be with respect to time. So that's why we come up with this part right here. So we have to take the derivative of both sides, but it has to be with respect to time. Okay, so in the left-hand side, we get the derivative of y with respect to t is dy over dt. And here, we are going to use the chain rule. So if we look at this here, this would give us negative 2x. And you can see that right there. But x and t don't match. And so that's why we have to use the chain rule here. And so when we do that, we're then left with dx over dt. Okay, so that's differentiating, and we use our chain rule. Now, in this case, we have to try to get dy dt by itself, because that's what we're trying to find. And in this case, it is. So you might want to add, solve for what you're looking for. So in this case, dy dt if necessary. Now that we have this relationship of the rates, we can go ahead and solve by substituting our known values to find dy dt. So given in the equation, we knew x equals 2 right here. So we're going to let x equal 2. And we also knew that dx dt was 3. So I'm just going to rewrite it there for you. And you can see here, all we have to do is substitute them into this equation up here. So 2 in here and then 3 in here. And then solve it. And so dy over dt is negative 12. Okay, so what that tells me is as x is increasing 3 units per time measure, y is going to be decreasing 12 units per time measure at x equals 2. All right, let's try another example. So suppose x and y are both differentiable functions of t, we talked about what that meant, and are related by the equation y equals x squared minus 3x. And we're asked to find dy dt when x equals 3, given that dx dt equals 2. So what we want to do here is rewrite our original equation. We get y equals x squared minus 3x, and leave a little bit of space here, because our next thing that we're going to do is actually take the derivative of both sides. So we want the derivative with respect to time. And that's really the key to these problems. Okay, now to solve this one, we are just going to be left with dy over dt. In this case, we're going to take the derivative here and then remember the chain rule. So if we look at this, that's going to give me 2x minus 3. Okay, just using our power rule. But then we're going to have to multiply by the derivative of x with respect to t. Alright, so now at this point we've taken the derivative of both sides, and we are looking for dy dt, and you can see it's already been solved for right here. And so all that's left now is to substitute in x equals 3 and dx dt equals 2. So this is going to be 2 times 3 minus 3 times dx dt, which is 2. So overall here we get 6 minus 3 is 3 times 2, and we get 6. So dy over dt equals 6. Alright, I want you to try this one on your own here. Go ahead and pause the video and then come on back when you're done to check your work. Alright, welcome back. Let's go ahead and check your work. So first thing you should have done is rewrite the equation and then take the derivative with respect to time on both sides here. Then use implicit differentiation, so you should have gotten dy over dt. Use the power rule here, so 3 times 2 is 6, 3 minus 1 is 2, so 6x squared, and then the derivative of 4x is 4. And then we got to have the chain rule, so we have dx over dt right here. Now the problem told us that x was 1 and dx over dt was 2, so we just substituted those in right here. Here's your x equals 1, here's your dx over dt, which equals 2, and then the rest is just simplifying. So 6 plus 4 is 10 times 2, and so your dy dt is going to be 20. Okay, so as x moves 2 units per time, okay, y is going to be moving 20 units per time. Alright, let's move on and look at some actual word problems now. Okay, so in this example, a pebble is dropped into a calm pond and it causes ripples in the form of concentric circles. So you can see the circles going out. Now the radius, which is r, of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area, okay, A, of the disturbed water changing? So what it's asking us is, let's compare R with A. So we're going to compare the radius to the area. And if we can come up with some sort of relationship there, then we know that our derivatives will also be related. Okay? So the trick here is finding that relationship. Now we have a little thing here that's going to help us remember how to do these problems. So we can see dreads is what we're looking at here. So D, R, E, ds. So this is how we're going to set up our problem, and we're going to start by making a diagram and then writing down the rates, coming up with an equation, differentiating, and then substituting. So the first thing we needed to do was make a sketch and label all known quantities. So really what we're dealing with here is a circle with the radius, and I put a little arrow here just to show where the radius is changing. So this is growing. Okay. Now we move on and we identify all our known rates and rates to be determined. So what does it tell us here? It says the radius is increasing at a constant rate of 1 foot per second. And so that information is going to be right here. Okay, so dr dt equals 1, and that's feet per second. Now it says when the radius is 4 feet, at what rate is the total area changing? So what we're looking for is the rate of change in the area, and we're going to write that as dA over dt. And I just want to put a note when r equals 4. Okay, so that's how we go ahead and write the rates. Next, we need to come up with an equation that relates the variables. So if you remember up here, we were talking about the radius being related to the area. Well, is the radius of a circle related to the area of the circle? Well, it is. And it gives us our formula right here, A equals pi r squared. So that is the relationship between area and the radius. Once we have this equation that relates our quantities, we differentiate. So we differentiate both sides of the equation implicitly, and then we use the chain rule with respect to time. So everything's got to be d over dt. So we can see here we take the derivative of both sides, To do that, we just get dA over dt, and then using our power rule, 2 pi r, and then dr over dt. Now, one note here is we're looking for dA over dt. And in this case, it happened that it was already solved for. So just want to put a note here that you're going to solve for what you're looking for if necessary, okay, or if needed. And that's going to be true of any problem. You could have them combined over here. They could be all over the place. So keep an eye out for that. Once you have this solved for dA over dt, what we're looking for, all you need to do is substitute all known values and then go ahead and find the rate of change we're looking for. So we know that the radius was 4, so we just substitute that in right there. And then we knew that dr over dt was 1, and so we substitute it right in here. When we do all of this, we end up with 8 pi. So when the radius is changing at a rate of 1 foot per second, we know the area is increasing at 8 pi feet per second. Alright, let's go ahead and try this one together here. It says the base of a triangle is increasing at a rate of 2 inches per minute. If the height is always 3 times the base, how fast is the area changing when the base is 6 inches? So we know we're going to be dealing with a triangle, and that's about all we have to draw. So let's go ahead and draw our triangle. And we have a couple things that we're working with here. We have a base and a height. Okay, so we see something here, there's a base and there's a height. So we're just going to make the base, you can call it x, it doesn't really matter. And then here's the height of our triangle. We're going to call this y. Now there's also a little bit more information here. It says the height is always 3 times the base. So when they give you that extra information, you want to see if you can write this in as few variables as possible. So what can we write? Well, if the height is always 3 times the base, we would know that y equals 3x. Okay, so we really have the base is x and the height is 3x. Okay, so this was drawing our diagram. Next, we want to write out any rates that we know. So they said the base of a triangle is increasing at a rate of 2 inches per minute. So the derivative of the base with respect to time equals 2 inches per minute. And what we're looking for, how fast is the area changing? Okay, so what we're looking for is the derivative of the area with respect to time. And they give us the information that when the base is 6 inches. So when x equals 6. Okay, so this is writing our rates in that dreads. Next, we want to come up with an equation. Okay, so we need an equation that's going to relate this x right here with this area right here. Okay, that's what we got to do. And fortunately, we know the area of a triangle is 1/2 base times height. So that's a good place to start. And let's see if we can relate that with x. So it's 1/2. The base is x. And the height is 3x. So you can see it was very important to rewrite this in terms of x, because that's all we care about, relating x with a. And now we've done it. And we can just simplify this here, get 1/2. Oh, this would actually be 3/2 x squared. Okay, so this was coming up with our equation to relate the variables. Next up, we need to differentiate this, because if a and x are related, then the derivatives are also going to be related. So let's go ahead and find the derivative with respect to t of both sides. Now you may feel like this is a tedious step, but it's really important in understanding the process of what's going on, being able to go back and check your work. So I encourage you to write this out. Okay, so let's take the derivative. We get dA over dt equals, and we're just going to use our power rule with the chain rule. So 2 times 3 halves is just going to be 3, and then x to the first, and then times, okay, since this is with respect to t, we still have a dx dt. All right. Now we just want to make sure that what we're looking for we actually have solved for. And we're looking for dA over dt, and you can see that we have solved for that right here. Okay, so there's nothing else we need to do. So that was finding the derivative. So I'm going to put a d there. And the last thing is substituting in. So we knew x was 6. We're just going to plug that in. And we knew dx dt was 2. So we're going to substitute that in. And so our final answer, the derivative of the area with respect to t, so this is how fast the area is changing, is going to be 36 inches per minute, and since it's an area, squared. Okay, so we know the base is increasing at 2 inches per minute, making the area increase at 36 square inches per minute. Okay, and so the last thing we had done here was substitute in our variables. Alright, now I want you to try this next one on your own. See if you can follow the whole DREADS pattern. Diagram, rates, equation, differentiate, and substitute. Okay, go ahead and give this a try on your own. You can pause the video and come on back when you're done. Alright, welcome back. Let's go ahead and check your work. So you should have had a drawing of a sphere, and pretty much the only thing you need in a sphere is its radius right here. Then, writing out the rates from the problem, they said that the volume was changing at 4.5 cubic feet per minute. Now, how did we know this was a volume? Well, a couple hints. It says cubic feet, so we know that's volume, and then air is being pumped into the balloon, and the air has volume, so that's what we got there. Now they asked us to find the rate of change of the radius. So there's our radius right there, when the radius is 2 feet. Okay, and so when we're trying to make our equation, we see a v here and an r here. So our equation needs to contain only a v and an r. Well, which equation do we know relates volume with radius? Well, this one right here. So volume is 4/3 pi r cubed. And so you can see the r here, and the v here. That's your equation. Next is differentiate. And so take the derivative with respect to time, both sides. And then you get some more practice with using implicit differentiation. So we got dv over dt, and then we got 4 pi r squared dr dt. Okay, so again, the 3 times the 4/3 gave us our 4, and the pi, and then r squared because it went down by 1, and dr dt because of the chain rule. Now this one, hopefully you caught this. You actually had to solve for dr dt, because if we look over here, that's what we're trying to solve for. Okay, so we had to isolate this guy right here and get it by itself. Okay, so that is our goal based on this. So to do that, you just simply had to divide by the 4 pi r squared on both sides, Okay, and then I just rewrote it so that the dr dt was on the left side right here, and then all of this stuff was on the right. So we had dv dt divided by 4 pi r squared, and I just rewrote it as times 1 over 4 pi r squared. It doesn't really matter, you could have left it like this. Then the last part would have just been solving, and so we had dr dt, and we substituted in dv dt, which they gave us right here, was 4.5. So here is 4.5 that we subbed in. And then we also were told that the radius was 2. So here's the 2 that we subbed in. Now this just becomes a calculation. You can put it in your calculator and get an approximation, and it was 0.09 feet per minute. Now because we're looking for the radius, it is just going to be in feet, and so there we related the two rates. Alright, there's some more examples in your packet. If you have the time, you can give it a try. Otherwise, we'll go through them together when you come back to class. So thanks again for watching, and we'll see you a little bit later.